Hello, everyone, and thanks for joining us, with an especially warm welcome to those joining us from COP27. I'm Charles, your host and a member of the Open Air Collective. Open Air is a global volunteer advocacy and open source research network with a focus on advancing carbon removal technology and policy. I'm joined today by Professor Susanna Garcia and Professor Bernd Smit, who are from the Heriot-Watt University and EPFL, respectively. They'll be sharing today about their PrIsMa project, a new direct air research project, and more importantly, about how you can get involved. So with that, take it away, Susanna and Bernd.
Thank you, Charles. It's really a pleasure to present to you some of the work we're doing in PrIsMa, and we will talk about that later, what that implies. So the topic will be on direct air capture. And the way we see it is there are three very important reasons why we need to do research to do direct air capture better. And when I mean better, it means we need to do that as cheap as possible and as quickly as possible because there is a big need. And we will go through those 3 points. But the first point is we need to some kind of insurance against a society that cannot get rid of its addiction to fossil energy. It's also an essential tool, as we will argue, in a net zero society. And finally, if you look around, we use all kinds of chemicals that contain carbon. And at present, the plastics, the clothes we wear, you can't look around if you see chemicals that are made from fossil fuels. And eventually, we want to decarbonize the chemical industry. And why should we use fossil fuels if we have too much carbon in the air? So these are three very important reasons why we do research on carbon capture, why it's such an important topic. But this is now something I would like to discuss. When I started working on this topic, that was something very new to me. And that is, if you think about what would happen if we don't have control of our addiction to fossil fuels. So let's just think about this virtual scenario that we have, and it may not even be that unrealistic if you look at the US elections, what may happen, that we have ideas that let's just ignore all problems and burn all our coals. What do I mean with all coals? What we mean there is there are no reserves, and just let's assume we're not restricted to anything and just burn that. And if you think about that, so if you think that we're talking about big numbers, we have already emitted 500 gigatons of carbon in the atmosphere. And but that's there's actually much more. We still have fossil fuels reserves that are 10 times bigger. And let's just assume that we have two scenarios. One is a moderate scenario where we just do 20% of all those known fossil reserves. We will burn that. It's not all the coal we have, but only 20%. Or you can also have a reserve, which is basically 5,000. And this is then a scenario you can have where here you have the years on this graph, and here you have the emissions. And what you see here in gray, these are these typical scenarios from the IPCC report, from the old one. The A2 is business as usual, and you see this enormous increase in use of fossil energy, or you see some control. So you see that our scenarios of burn all coal, the red one, or only 20% of that total amount are not that unrealistic, that over a relatively short period, say, we burn all those reserves. So what will actually then happen? And that is illustrated here. So if we do that, now what? What you then will see is of all the CO2 we emit in the atmosphere, we'll get more biomass, and the ocean will pick up a little bit of that CO2. And because of that, 40% of the CO2 we emit in that atmosphere will immediately disappear. More plants, more dissolved in the surface layer of the ocean. But then and that is sort of illustrated here, then it takes a very long time, of the order of 5,000 years, before it really gets to zero, before we get to the levels from before the Industrial Revolution. And that has to do with this process here, that there is a very slow exchange between the surface layer of CO2 and the CO2 in the deep ocean. And that mixing goes so slow that the CO2 stays in the atmosphere for over 2,000 years. And that is such an important message. And that is something, it stays there for a very long time. And people have modeled that effect on the climate. So what you see here is the time, and here the CO2 concentrations in the atmosphere once we have burned 20% of our coal reserve. And you see all these lines, and these are the different climate models. So what you see is there is uncertainty in the science of when we will reach, say, a level of, again, of say, 450 ppm. That can happen earlier or later, but it will take an awful long time. And if you look at the consequences, this is where we are now. And this is the level of CO2 where there is no ice anymore on the poles. So you see, if we overshoot the CO2 levels, it takes a very long time before nature takes care of it. And the only way we can do with reducing these levels, if we overshoot, is getting the CO2 directly out of the atmosphere. So, and that is basically what I call this direct air capture is the only insurance we have against this much stupidity of burning all our coals. So this is sort of the worst case scenario. If we don't do anything, this is the only thing we can do to get those CO2 levels down. It's very expensive because it's 5 times more expensive to capture a CO2 molecule once it's in the atmosphere than capture it at the source. But it's something we could do on a very large scale if we are that stupid in burning 20% of all our coal reserves. Hopefully, a more realistic scenario is if we go to net zero. And that is something you will hear many times at this COP. We just want to live in a society that everything we do, nowhere there should be a CO2 molecule that is allowed to escape in the atmosphere. So that is the theory. But what we will see is that some industries are really, really difficult to decarbonize. Think about aviation, think about cement, think about steel. There will always be a little bit of losses of CO2 in the atmosphere. But that's not a problem because we can solve that by capturing that CO2 directly out of the atmosphere. So in this net zero, to make it really net zero, you always need to capture a little bit of the CO2 to take care of this missing part. And that is also a matter of economics. At a given moment, it's just cheaper to get it out of the air than trying to squeeze the last few percent of those other things. And finally, CO2 is a source of carbon we have too much. So why use fossil fuels? And that becomes interesting because now, instead of CO2 seeing as a problem, it's a resource for carbon. So what we can do is, if you think about the circular economy, you can never recycle for 100%. You want to do it as much as possible, but you will always lose a little bit. So we need this source of carbon. Why not get it from the air instead of fossil fuels? And that will give us all kind of exciting new chemistry we need to work in on the coming years. And it's the same. Aviation fuels will be very difficult to see, but we can make it from air, the carbon, and from water. Air as the source of carbon and water as the source of hydrogen. And how are we going to do that? That's something where Susanna is going to talk about now if we talk about PrIsMa. Susanna?
Thanks very much, Darren, and welcome everyone. I'm delighted to be here as part of the PrIsMa team to explain a little bit what we are trying to do in this fantastic project. So, as Darren has just mentioned, we need to make sure that we indeed remove all the carbon from all the potential sources that we have around the world. So what you see here in this slide is basically our starting point in the PrIsMa project. And just in case you are wondering, PrIsMa stands for Process Informed Screening of Materials for Carbon Capture. So this is a multi-collaborative project, international project, where a lot of partners come together to try to address the following question. So we do have a wide range of CO2 sources around us, and you have some examples here on the slide. Yeah, we need to decarbonize our power production. We need to decarbonize our industries. There are a lot of also smaller scale carbon emitters like waste incinerators, biogas plants, and eventually we will also need to remove CO2 from the air. So all of those different CO2 sources have indeed many different characteristics. So the concentration of the CO2 in each of them is different. They do have different pressures, different temperatures. So a lot of different things that we need to know as engineers when it comes to designing a process that can deal with them. On the other side, we also have a very wide range of CO2 sinks. In other words, what are we going to be doing with our carbon dioxide once we separate it out from the gas stream or from the air? We need to do something with it, but always making sure that indeed we are reducing or removing our carbon emissions. So equally then, on that sink side, we can send, for instance, carbon dioxide for geological storage. So it's injected deep underground and will remain there, or we can make use of that carbon dioxide as a chemical vector to, for instance, produce things like fuels or chemical products or any other type of product. So then the question then here that we asked ourselves a few years back was, for a given then source and a given sink of CO2, and also for a given region in the world, right? Because we are all placed across the world, and where we are is indeed very important. It's going to make a big difference to answer this question. So what's the optimal separation process for that given combination of a CO2 source and CO2 sink? So here is when PrIsMa kicks in. And basically, what we are trying to identify here in this project, or what we are trying to answer, is what's the optimal material, first of all, for that separation, and what's the optimal technology. So the consortium has a wide range of experts covering all the important aspects, not only from the material side of things, but also, of course, from the engineering side, because really that integration is needed in order to answer this question. So then if we focus specifically on direct air capture, then our carbon dioxide source is fixed. We want to remove CO2 from the atmosphere where the concentration of CO2 is approximately 400 ppm. So it's really, really very small concentration there. And then the question is, depending on where we are going to be then sending that CO2 to, what's again our optimal material, what's our optimal process, and how is it going to affect the selection of region when it comes to the performance of that direct air capture plant? So all these questions are our challenges. It's a big challenge to get to know how to go about answering the questions, but it's also a tremendous opportunity when it comes to developing all the science, all the technology that is required in order to get us to net zero. So before I go a little bit into the more nitty-gritty of what we are doing in PrIsMa, I would just like to explain very briefly what is the type of technology that we are considering here to remove or to separate the CO2 from the air. And the technology is called adsorption. So it's basically a gas-solid separation technology. So what we are doing here is we are putting in contact our carbon dioxide, which is the gas, And we put that in contact with a solid, a porous material. And you can think of it like a sponge type of material. So really a porous solid material that contains a lot of spaces inside the material. And all those holes, all that space in there will be able to accommodate our carbon dioxide. So the way it works in the real world, when we go about, putting all of this in practice in a direct air capture plant, is that we will have what we call our reactor or our contactor, where we put our material in, and then we will get our air through that contactor or through that bed, and the CO2 will be able to stay in the material. And again, this is down to the science behind that. Our material is able to has affinity for that CO2, and ideally only for the CO2. So everything else that comes in the air gets through, and only the carbon dioxide gets retained in our direct air capture unit. But once it's there, we of course need to make sure that we get it out, right? Because the idea here is that we keep using the same carbon capture material over and over again. So, because of course that will reduce our cost, and for an awful amount of reasons that we want to make sure that we keep recycling the same material over and over again. So it's important that everybody realizes here that this is a cyclic process, and a cyclic process that is made up of this very first step of retaining your CO2 on the material, which is the capture step. And then eventually you need to get it out in order to either send it to geological storage or to make use of it for the production of fuels or whatever your sink is. So for getting it out, what we do is we make use of thermodynamics and things we know that will kick out that CO2 from our material. And something we can do is we can apply heat. And we know that by applying heat to our contactor, the CO2 will come out. So in short, it is a cyclic process where that is made up of a continuous adsorption, desorption, or regeneration steps. So adsorption, we retain our CO2 in the material. Desorption, we get it out by applying heat, by reducing pressure, by a series of mechanisms that we understand and we know we can do. So, okay, so those are the fundamentals of the process, how, in very, very simple terms, how a direct air capture process based on solid sorbent materials works. Now, the next question is, what's the best then material to start trying different things out here when it comes to what would be the optimum material for the separation? And what we are doing in PrIsMa is we are focusing on metal-organic frameworks as our star materials for carrying out this separation. What are metal-organic frameworks, which are commonly known as MOFs? So these are a really fantastic and beautiful materials that are crystalline, and one of the main characteristics that they have is that they have their porosity, so the amount of space that the material contains to indeed retain that CO2 can be huge. And it's in MOFs, what we have, you have a representation there. It's a 3D structure that basically connects metals that are shown there with organic ligands. So those metals in the structures are connected through ligands, and that gives us many different types of pores or spaces material, and also it gives us the flexibility of playing a lot with the chemistry. And the reason for this chemical flexibility that the MOFs provide us with is because we can do many things from the chemistry point of view. So we can start just by changing the metal. So what you see there as a purple kind of diamond is our metal in this specific case. And instead of having a particular one, for instance, iron, you can play and insert there a different one like magnesium, calcium, whatever. Equally, you can also change the linker. So you can change those connecting rods in between the metals. And there is, again, a huge variability or a huge opportunity here to play with many different linkers. But the third thing we can also change within this type of materials is the pore topology. So the shape of your pores, again, depending on how you engineer the material. And all these things will have an impact on the type of material that you synthesize and its performance. So basically, in terms of chemical space, the idea of working with MOFs is just fantastic, because what it gives us is all the opportunity to explore the chemical space and interrogate it in order to find that optimal material for a direct air capture process. But of course, now the question is, out of those hundreds of thousands of potential structures, because you can probably quickly figure out that just by doing all those potential combinations of metals, of ligands, and of topology, you end up with a huge chemical space. And when I say huge here, I really mean like, in theory, millions of different potential structures. So this is something that the research community has, has asked themselves for many years. And there are, if you go to the literature, you will see a lot of reported structures when it comes to carbon capture applications and direct capture applications that try to claim the best material for the separation. So that's kind of what has been going on for many years now, right? Like, yeah, my material is the best one because of X, Y, and Z, and different group, different organization claiming the same thing. But basically, all of these claims have been based on very, very simple metrics. And it is very well known that material scientists and engineers, we have all failed tremendously in bringing all these aspects together in order to make sure that all these fantastic materials indeed can make it to commercial deployment and make a difference in the real world. And that's exactly what we are trying to address in PrIsMa. So the vision of the project is to develop a platform, and this is what is represented here in this lovely schematic, is to develop a techno-economic platform where we basically go about materials discovery, our materials discovery process. So basically we interrogate that materials space that contains hundreds of thousands and potentially millions of different structures, but we do that by being guided by the requirements of the process. So we very firstly look at the whole chain when it comes to what is going on. So basically our CO2 source, our CO2 sink, we understand the system, the whole system first. And once we understand that, so we need to look at things like, of course, like the life cycle assessment of our materials, of our products, of everything that is going on. And we also look at the techno-economics involved in your separation process, and the type of process that we need to have in place for, in this particular case, for removing CO2 from the air, and then depending on where you are sending that CO2 to the sink, and then eventually all of that will inform our materials discovery process. So again, this is a massive initiative that we have started 3 years ago now, and that is funded by the ACT program, and as well as some funding from the Zürich program. And we are very fortunate to have all this massive amount of expertise around to sort of address this huge challenge. So if we move on now on to the outcome of all of these. So yeah, basically we have developed all the science and all the technology, and we have filled in all those different layers that you have seen in the previous slide to put together an online platform. So this is an online open access platform that will basically inform everyone about what would be the optimal material for an optimal application. So it will solve this question that it's been hanging around for many years in terms of, we have far too many materials. We cannot, of course, test them for all different applications, but we now have a tool in place that is able to tell us, okay, for a given source, in this case, direct air capture, so for this specific separation, what out of all these hundreds of thousands, potentially million structures, what are the top performers that we should be focusing on? And this is something that we exemplify here in this diagram with by just representing a couple of different performance indicators where we are indeed targeting the very low area of the graph, and those would give us the best performance and the best material. And we then are able to identify which materials are those. So this is then the power of the PrIsMa platform, and this is really what we would like to communicate to you all, and which we would love that you get engaged with.
So what you see, what Susanna has explained, we now have a mechanism, a tool to evaluate materials, to see how well they performed. And for example, what is very interesting, if you look back at the previous slide, the top performing materials, and that is sort of shown here, they were developed for iron detection or degeneration of organic pollutants. Nobody that made that material ever tested it for direct air capture, but PrIsMa has identified these materials as very promising. So we need to look at them. But there are now algorithms where we can generate also these materials well before they synthesized on a computer. And that is really interesting. And with these algorithms, we can actually generate trillions of novel materials. But it's extremely time consuming. It's extremely difficult for us to evaluate all those materials. So what is now the idea of this call for action is to ask for your help. Can you help us in evaluate these materials on your computer? What the plan is of PrIsMa to make programs available that you can build a material, that you can put it in the computer, and that you can tell us how good it is. And in that way, with that machinery, you see the machinery wheels and the metal organic frameworks within the wheels of the machinery. We can evaluate these materials and we can sort of see if there are some good ones, and we need your help for that. The other problem we have, and that's the experimental problem, and that is something Susanna can explain to you.
So the next, the second call for action here really has to do with how to operate a direct air capture plant anywhere in the world, right? And what's the impact of any regional constraints, and for instance, things as simple as the weather on the performance of the material. So being able to screen and rank materials on the computer with all the right metrics is great, and that's what the PrIsMa platform allows us to do. But eventually, we also need to validate all those predictions. And that's exactly what we are doing in this second part of the challenge. We just want to then, that beautiful material that we have anticipated is going to perform great for direct air capture, we want then to validate those predictions in the lab. So we are just going to place the sorbent material into an experimental setup. We are going to get air through that contains CO2, and then we should be able relatively quickly to understand how well and how good that material is for direct air capture.
So what is then the plan? The plan is that either you engage with the computer, where you use these building blocks. You see here the metal nodes on one side, the linkers on the other side. You put them together, you evaluate the material, and then the hope is that some of the promising materials we can then synthesize and we give them to Susanna. and they can make that. So this is then the idea. Hey, you synthesize the material or on the computer, and then you rank them. And maybe it works for carbon capture for coal-fired power plant, or for natural gas, or for direct air capture. And you see that's illustrated here. No, not very good. The material not very good for coal. Not very, maybe for natural gas, worth trying. But here we have a winner for direct air capture. And if you then have a winner, we can try to synthesize the material in the lab, and then somewhere else in the world, it can be tested. And that is sort of illustrated here. And you may recognize the person who is behind this machine. Susanna, can you comment a little bit of what you're doing here?
Yes. So what we will try to do here then is to make sure that everybody has access to what we call the PrIsMa toolkit. So basically, this will be a very simple kit that will allow us to estimate how good the material performs for direct air capture applications. So basically, we will be able to measure the performance of the material pretty much anywhere in the world. So and then you can then report back to the platform all your findings. So it will help us tremendously to collect the data, the performance data that we need to validate the predictions on any of those fantastic top performing materials that will help us to solve the direct air capture system and to solve the problem of removing CO2 from the air. And will also help us understanding things like the effect of the specific climate in your specific city or your specific region in the performance of the material and so many other things. So we are very, very excited with having as many of you on board as possible in these two challenges, and we really hope that you participate and that you get in touch to help us solve this huge problem and challenge of removing CO2 from the atmosphere.
Yeah, and we will be extremely excited to be able to report next year what the progress is. And hopefully this initiative of open air will help us solving this very urgent problem of reducing CO2 emissions. And all our research has been made possible by a very generous donation of the Grantham Foundation that allows us to extend this PrIsMa platform to direct air capture. And the Grantham Foundation would be delighted to see how much you will help us in getting towards a reduction of the CO2 levels in the atmosphere.
Yeah, so thanks for sharing about your work with us, Bernd and Susanna. This is a really exciting opportunity to democratize research in direct air capture and give everyone a way to help contribute in finding solutions to reach net zero. If you want to stay up to date on the PrIsMa project and opportunities to get involved, you can click on the link in the description to sign up for a mailing list, which Bernd and Susanna will be sending out updates on how you can help out, as well as progress on their project. Open Air Collective also has a Discord server if you're looking to join a carbon removal community. That's also in the description. And so thanks for joining us, and we're excited to hear about all the awesome work from COP27 to reach net zero.